Everyone keeps asking the wrong question. They ask whether China can replace ASML. Very few ask whether China has started solving the problems ASML wasn't measuring in the first place. Those are completely different questions. For years, the global semiconductor conversation has revolved around one machine: extreme ultraviolet lithography. EUV became the symbol of technological supremacy. If you had it, you belonged to the most exclusive manufacturing club on Earth. If you didn't, you were supposedly years behind. That narrative was simple. Reality rarely is. Because making a transistor isn't only about drawing smaller lines onto silicon. It's about checking whether those lines are exactly where they should be, millions of times, across a wafer nearly the size of a dinner plate. If your measurements are slightly wrong, your expensive chip is nothing more than polished electronic scrap. That's why companies spend billions not only on lithography, but also on metrology, the hidden science of measuring structures so tiny that visible light isn't even useful anymore. Here's the strange part. Almost nobody outside the industry talks about metrology, even though every advanced chip depends on it. Without accurate measurement, precision manufacturing becomes educated guesswork. And that brings us to a development that received far less attention than another export control headline. Chinese researchers and engineers, working alongside domestic equipment companies supporting manufacturers such as SMIC, have been investing heavily in computational metrology, advanced defect inspection, and AI-assisted process control. None of those sound as dramatic as an EUV scanner worth over $350 million, but they solve a different problem, a potentially bigger one. Because if sanctions make the world's best equipment harder to buy, the next logical move isn't always to copy every machine. Sometimes it's to redesign the workflow. Think about aviation. You don't necessarily build a faster airplane by installing a larger engine. Sometimes you redesign the wings because physics gives you a cheaper advantage. Semiconductor manufacturing works surprisingly similarly. Washington's export controls largely focused on preventing access to advanced lithography systems, high-end inspection tools, and cutting-edge chip-making equipment after measures introduced in 2022 and expanded over the following years. The assumption was straightforward. Deny enough hardware and technological progress slows dramatically. That assumption wasn't irrational, but assumptions have expiration dates. One dry observation deserves mentioning here. Governments often measure sanctions in policy documents. Engineers measure them in workarounds. Guess which group usually works weekends? What fascinates me isn't the claim that SMIC has somehow overtaken ASML. The evidence simply doesn't support that. ASML still leads the world in EUV systems, and companies like KLA and Applied Materials remain dominant in process control and inspection. The interesting question is different. What happens if China discovers that some bottlenecks don't disappear, but become less important because the manufacturing philosophy itself changes? That's a much harder possibility to measure. And ironically, measurement is exactly what this story is about. Because buried beneath headlines about lithography lies a quiet technological race over algorithms, defect detection, computational imaging, and manufacturing intelligence. It's less glamorous. It's also where the next surprise may already be unfolding. And once you see how this invisible layer fits together, the competition between ASML and SMIC starts looking far less like a race for one machine, and much more like a race to redefine what winning actually means. The easiest mistake to make is believing semiconductor manufacturing is one giant machine. It isn't. It's closer to an orchestra. Lithography, deposition, etching, cleaning, inspection, packaging, software, chemistry, optics, every section has to play at precisely the right moment. One instrument doesn't carry the performance, timing does. That matters because SMIC has spent the last several years adapting to a reality that few manufacturers would voluntarily choose. No EUV, at least not commercially available from ASML. Instead of waiting for the restrictions to disappear, SMIC doubled down on deep ultraviolet lithography, DUV, combined with multiple patterning. Engineers expose the wafer several times rather than once, gradually building features that approach the dimensions normally associated with more advanced equipment. It's slower, it's more expensive. Yield becomes harder to maintain, but harder isn't the same as impossible. This is where measurement quietly becomes the deciding factor. Every additional patterning step increases the chance of tiny alignment errors. Imagine stacking 20 transparent maps on top of each other. If each one shifts by only a fraction of a millimeter, the final image becomes distorted. On a semiconductor wafer, those shifts are measured in nanometers, thousands of times smaller than the width of a human hair. Finding those errors early determines whether a chip survives production. Companies like KLA built global leadership precisely because of this expertise. Their inspection systems don't manufacture chips. They tell manufacturers where things are going wrong before defects multiply across thousands of wafers. But hardware is only half the equation. The other half is software. Increasingly, artificial intelligence is being trained to recognize microscopic defect patterns long before human engineers notice them. Every production run generates enormous amounts of data: temperature changes, vibration signatures, optical images, plasma behavior, chemical variations. Separately, each data point means very little. Together, they form a digital fingerprint of the manufacturing process. Chinese firms have invested heavily in that fingerprint. Organizations including the Chinese Academy of Sciences, alongside domestic equipment makers such as Nora Technology Group and Advanced Microfabrication Equipment Inc., AMEC, have steadily expanded research into process control, inspection technologies, and computational optimization. None of these companies receive the same public attention as ASML. They don't need to. Their role is different. Rather than replacing one iconic machine overnight, they're reducing dependence on foreign technologies piece by piece. Think of it as replacing bricks instead of demolishing the entire building. There's historical precedent for this approach. Japan followed a remarkably similar philosophy during the rise of its precision manufacturing industries in the 1970s and 1980s. Instead of immediately dominating finished products, Japanese firms mastered materials, tooling, precision components, and manufacturing quality. Eventually, those quiet advantages became difficult for competitors to match because they were embedded throughout the production chain. China appears to have learned that lesson, not by copying Japan exactly, but by recognizing that supply chains reward consistency as much as breakthroughs. Of course, critics make an important point. SMIC still cannot mass produce at the same scale or efficiency as TSMC's most advanced nodes. Yield rates remain debated. Manufacturing costs are higher. Export controls continue limiting access to premium inspection tools, advanced design software, and leading-edge manufacturing equipment. Those constraints are real. Ignoring them would tell only half the story. But there's another side that's becoming harder to dismiss. Every year spent solving engineering problems under restrictions creates experience that cannot simply be purchased later. Engineers become accustomed to optimizing around limitations. Suppliers improve because customers have no alternative. Universities adjust research priorities to fill missing technological gaps. Necessity has an unusual habit of producing expertise. Not always, but often enough that history keeps repeating the pattern. Which brings us back to that overlooked word from earlier: measurement. Because if manufacturing intelligence becomes increasingly driven by software, algorithms, and AI-assisted process control, instead of relying exclusively on hardware superiority, then the competitive landscape starts shifting beneath everyone's feet. And that's where one recent development forces an uncomfortable question that reaches far beyond SMIC itself. The assumption behind many export controls is surprisingly simple. If the leader keeps pulling farther ahead, the follower eventually gives up. History doesn't always cooperate with that theory. Sometimes pressure delays progress, sometimes it redirects it, and every so often, it forces people to solve a completely different problem, one their competitors never had a reason to tackle. I think that's exactly why the semiconductor race has become far more complicated than the headlines suggest. Look at Huawei's Mate 60 Pro launch in 2023. The phone wasn't shocking because it contained the world's most advanced chip. It didn't. The surprise came from the fact that many analysts believed producing a domestically manufactured 7-nanometer class processor under existing sanctions would be significantly more difficult than it turned out to be. The phone became a symbol, not because China had caught up, because the gap proved less predictable than many expected. That distinction matters. It also exposed something else. Western analysis has traditionally measured success by one metric: process node leadership. 3 nanometers, 2 nanometers, eventually 1 point something. Those numbers are important, But they don't automatically answer the question customers actually care about. Can enough reliable chips be manufactured at a competitive cost? That's a manufacturing question, not just a lithography question. Suppose Factory A produces the world's most advanced chip, but struggles with production costs. Factory B manufactures a slightly older design, achieves consistent yields, improves inspection through AI, and supplies millions of processors that satisfy most commercial applications. Who wins? The answer depends entirely on the market you're talking about. Data centers training frontier AI models demand the absolute best. Cars don't. Industrial robots usually don't. Smart appliances don't. Power grids don't. Most factory automation systems don't. Even a large portion of cloud infrastructure can tolerate chips that aren't sitting on the bleeding edge. That's why mature node manufacturing remains an enormous business worth hundreds of billions of dollars every year. This is where I think many discussions become too binary. Either China is years behind, or China has already won. Neither conclusion matches reality. The truth is messier. ASML remains indispensable for leading-edge EUV production. TSMC, Samsung, and Intel continue investing tens of billions into increasingly advanced manufacturing. Companies like KLA, Lam Research, and Applied Materials still possess decades of accumulated expertise that cannot be recreated overnight. Those advantages are genuine. Yet manufacturing isn't static. Artificial intelligence is beginning to influence wafer inspection, predictive maintenance, equipment calibration, and defect classification in ways that barely existed a decade ago. Instead of waiting until something breaks, algorithms can increasingly predict which production parameters are drifting before defects spread through an entire batch. That changes the economics. An engineer who solves one production issue manually helps today's wafer. An AI model trained on thousands of similar events may improve every wafer produced afterward. That's a very different kind of scaling. Here's the reversal that keeps coming back to me. Perhaps the biggest competitive advantage isn't owning every superior machine. Perhaps it's learning how to extract more performance from the machines you already have. Those aren't identical skills. One depends heavily on capital. The other depends heavily on engineering culture. I'm not completely certain where that balance eventually lands, but the evidence increasingly suggests that software and manufacturing intelligence will account for a growing share of future competitiveness. If that's true, the semiconductor race is gradually shifting from hardware supremacy toward system optimization. And that's a race where victories are much harder to see. Because they don't arrive with a ribbon-cutting ceremony or a billion-dollar machine rolling through the factory door. They arrive as 1% better yields, 0.5% fewer defects, minutes saved from production cycles, tiny improvements, repeated thousands of times. Individually, they barely make headlines. Together, they quietly reshape industries. Which raises one final question. If the world's attention has been fixed on the machine everyone could see, what happens when the real competition starts happening inside the software, the algorithms, and the measurements almost nobody ever notices? Here's the part I keep coming back to. The semiconductor race didn't become more complicated because ASML became weaker. It became more complicated because everyone else became more adaptable. Those are not the same thing. ASML is still the only company capable of shipping commercial EUV lithography systems at scale. That technological lead took decades to build, involving thousands of suppliers, optics from Zeiss, ultra-precise light sources, and engineering challenges that most industries never encounter. Nothing we've discussed changes that reality. But another reality is developing alongside it. The definition of leadership is quietly expanding. 20 years ago, whoever built the fastest machine usually won. Today, success depends on who combines hardware, software, material science, artificial intelligence, manufacturing discipline, and supply chain resilience into one functioning system. The best chip isn't always produced by the best machine. Sometimes it's produced by the best process. That's an uncomfortable distinction because processes don't generate dramatic headlines. You can't photograph an optimization algorithm. There's no ceremonial unveiling for a manufacturing workflow that reduces defects by 0.8%. Yet those improvements compound, day after day, wafer after wafer, factory after factory. Eventually, they become national advantages. I also think this explains why the semiconductor industry has become increasingly difficult to analyze from the outside. People see export restrictions. Engineers see design constraints. Investors see capital spending. Governments see national security. Factory managers see yield charts. All of them are looking at the same industry. They're simply measuring different things. And perhaps that's the irony hidden inside this entire story. The conversation started with measurement. Maybe measurement has also been the blind spot. If analysts focus only on transistor size, they may overlook manufacturing efficiency. If they focus only on lithography, they may underestimate process control. If they count only sanctioned machines, they may miss the software quietly making existing equipment more productive. That doesn't mean China has solved every challenge. Far from it. Advanced electronic design automation software remains dominated by Western firms. Cutting-edge inspection equipment is still led by established international companies. High-bandwidth memory, advanced packaging integration, and next-generation process nodes remain fiercely competitive areas where several global leaders retain significant advantages. Anyone claiming the race is already over is reading the scoreboard far too early. But saying nothing has changed would be just as misleading. The evidence points towards something more subtle. Instead of trying to recreate yesterday's semiconductor industry exactly as it existed, China appears increasingly willing to build a version that works within its own constraints. That approach may not produce leadership everywhere, but it doesn't have to. Global technology competition isn't decided by perfection. It's decided by whether a country can keep improving faster than its obstacles grow. That's a very different contest. Here's my view. Over the next decade, we'll probably stop talking about one company or one machine as if it alone determines technological leadership. The winners will be those who integrate dozens of disciplines better than anyone else. Lithography will still matter enormously, but it will become one chapter rather than the entire book. My prediction is that the next major surprise in semiconductors won't arrive because someone builds a magical new machine overnight. It will come from thousands of invisible engineering improvements that together shift the economics of manufacturing just enough for the rest of the world to notice, probably later than it should. So perhaps ASML's real blind spot wasn't underestimating a competitor. Perhaps it was assuming the race would always be measured by the same yardstick. History has a habit of replacing the ruler just before the results are announced. If you enjoyed this deep dive, subscribe and let me know which hidden technology race you'd like us to unpack next. The biggest shifts in the world are often the quietest ones.